Great. So there is a file called function under the folder source, which you can find on GitHub already. And I'm hoping that you already have pulled your GitHub and you can find this file. Can everybody confirm this, that they can see this function under? So if you have not done this, or if you do not have it, then what you can do is open a new terminal. And in there, you write git pull and press enter, essentially. And hopefully, once you do this, you will see a function, a file called function.lean. Kylie, do you have this? Okay. And I'm guessing, Sherry, you have that as well. Great. So that's a source file, which means like it has all of the things that I'm going to say today, plus more comments and more examples. So that is a file I would recommend you to study. And today, as usual, I'm going to do this demo file. What is a function? Which has some of the examples that can fit within the lecture time. Okay. So I imported two files from Mathlib. This is the first file. It's really defines. So in this file, the real numbers are defined. So we are not going to construct it, at least for now, the real numbers. And in this file, the square root is defined. Okay. So when I write open real, I'm essentially opening a namespace, but I want to talk about namespaces later, but let me write open namespace. So what this does is it makes available all the kind of API inside here in this file. So I don't have to write long names like real.py or something, right? Like real.add, I guess, would be a function. Wait. What's going on here? Okay. But let me start from here. Oh, my Lean is not responding for some reason. What is going on? Control-Shift-T, Lean4 restart file. Oh no, it's trying to build all of the Mathlib again. That is not good. So if such situations, oh no, so it's going quickly. If this, if such a scenario happens that this compilation, which was this orange bar disappearing, took long, by long I mean more than like 20 seconds, then you have to get the cache files from Mathlib. And there's a command to do that. It's called leg exe cache get. And that's, the command is explained inside one of the Zulib streams, essentially. But luckily, we didn't have that situation. So right now I have to, Lean works, essentially. So, okay, this is the type of natural numbers, which we discussed before. But now I want to define a function. And what is a function? A function is essentially a rule by which you give input to the function and function produces output for you. So it's a rule for producing output from input. So in this file source, I actually give quite extensive description of what functions are. But essentially, we can think of a function as a program that takes an element A of the input domain and returns a unique element, which is like F applied to A. So that's a new term of the target type B. Sometimes I'm going to say this function assigns element F of A So this is a new element to the element A of A. So what are examples of functions? So for example, a neural network is a function, right? So what a neural network does is it gets lots of data points. It also gets lots of parameters and weights for the nodes of the network. And at the end, it gives you some outputs, which classifies like an image. It can be binary, like it can classify something as a cat or a dog, or it can be like, 10 options, like 100 digits, classifies digits, right? And it tells you like which digits the text that has been read, essentially, which digit it can be. But the input, it can be like I don't know, 700 arguments, right? Some of them are weights of the network, and some of them are just the input data. So that's a function. Like light switch is a function, essentially. So the input can be like, the force that you put on it, and the output is the light coming off or on. So that's a Boolean output. So functions are everywhere, essentially, and in life, but also in mathematics. So that's why this is like maybe the most important lecture in the whole course. So today we are going to deal with functions in mathematics. And maybe a very simple function would be this function called successor. So the idea of this successor is like, I want to give an input to this function, like a natural number, and I want it to produce as an output the next number. So if I input 0, I expect this to be 1. So output is 1, while the input is 0. And similarly, if I evaluate it at like 1,000, here input would be 1,000, and the output would be 1,001. Okay, so this is the idea. The idea is like this rule that adds 1 to every element. The idea is like, how can we write this in Lean, right? So this is the fundamental bit that can be repeated everywhere. So you put the argument here. So that's the input, right? The output is n plus 1. That is what we want to see. And then there are 2 more symbols. There's this one, which is like arrow, and then there's fun. So fun specifies that whatever I'm going to write after it, it's going to be the rule of the function, sending n to n plus 1. The next thing that comes after fun is argument, or the input. The arrow, essentially, it's a way to tell Lean like whatever comes after this is an output, and then I write the output. So the output is essentially, you can also write it in brackets, makes no difference. Any question about this that doesn't make sense to you? Everybody was okay with this?
For when you identify n to be a natural number, what would happen if we didn't input a natural number? Would it output an error?
Very good question. So let's define alternative sock as to be fun, like sending n to n plus 1 without telling Lean that this is a natural number. And now we can actually check both of them. We can check sock. So sock says, well, yeah, given a natural number, sock of that natural number is again a natural number. And if I do, I think, at this, it tells me the whole type of sock, which is a function from, and by the way, functions are specified by arrows. So this object, n arrow n, means the type of all functions from natural numbers to natural numbers, right? And sock is a term of that type. So maybe copy this. I want to explain this better. So I'm going to copy this. So this means, so first of all, we have to define 2 things here, right? So this bit is the type of all functions from natural numbers. So how many elements can there be? Like, you know, when we had this type check bool, this type had only two terms, right? False and true. But my question is like, how many elements does this type have? Potentially.
Infinite many?
Right. I mean, you can, for example, you can produce many function which adds 2 to n, right? You can produce a function that adds 3, and you can continue this and you get infinitely many functions that way, at least. So this type has infinitely many elements, and one element in particular is this sock. So whenever we write this, we mean sock is a term of nat to nat. Or basically, another way to read this is sock is a function from natural numbers to natural numbers. Okay. So if we actually didn't explicitly give the type of n as a natural number, Lean would default it to natural number, and essentially the same would be true of sock alt, because we can check it now. And hopefully it says, yes, still from nat to nat. So that means in here, Lean automatically inserted natural number as the type of variable n. It's automatically inferred. Any question about this? Okay, if no, then I go further. Okay. Again, we have this command eval. So if I put a function, so we can check functions as we did here, but we cannot evaluate function. It doesn't make any sense because we usually evaluate function as at an input. So if we do sock eval, the Lean error is expression sock has type nat to nat, and then but instance blah 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 failed to be synthesized. Okay, some error that we don't understand, but essentially what it says is like it cannot evaluate functions. Or rather, Lean cannot evaluate functions without inputs. However, if you do evaluate it at an input, let's say 0, then hopefully we want to get 1. So this is the result of evaluation of function successor at 0. And by the way, this should be sock. Okay, let's define a little bit more complicated function, which is a function that doubles. So the rule is like, I want to double a natural number. So if you give me n, I want to give as output 2 times n. Again, I can specify it like this. I take an input n and I write an output 2 times n. And by the way, here I could have not included brackets and everything would work. So if I check double, I get this expression, which essentially says double is a rule. And here, if I do add, it gives explicit type of double, which is nat to nat. Any questions so far? Am I going too slow?
Wait, sorry, can you just click again? I just missed it. When you click on at double versus when you click on just check double.
So if I do check double, essentially gives me back the definition. Sort of like it gives me
I see.
type of the output, right? This is the type of the output.
Mm-hmm.
While here, it gives me the whole function type.
Okay, I see. Thank you.
No problem. But I mean, this double is an animal whose type is nat to nat, right? It's a new, like, you know, before we had these type constructors where like we had things like nat times net, right? And this was the type of pairs. So this followed this pattern of Cartesian product of two types. Like if I have types A and B, I can construct a new type, right? So this net to net is an instance of this type constructors. So maybe I should explain this in the comment, which is this sort of type construction rule. So if A is a type and if B is a type, then what I want to have is a new type, which is A2B, right? So that's, let's say, the formation rule. So how I form the type. But I also have to say what are the elements of A to B. So I need some introduction rule, right? And the introduction rule is a little bit more complicated, but essentially what it says is like, if from knowing A in A, I can sort of infer that f of A, so f of A is a new expression that depends on A, right? Is in B, then I can do this, introduce the function. So this is introduction rule, which says fun A to f of A is a function from A to B. So here I just constructed a new type out of A and B, and here I gave a way or a sort of a specification of the terms of the type A to B, right? So this should be compared to, if I go back to lecture on type, what is a type? I think I need to go to the source file though, yeah. So here, remember that's what we did, right? So here I gave a way to construct a new type out of two previous types. And this was a way to construct new terms of that new type. That was product type or Cartesian product type. And this time I'm doing it for function types, which is a different thing. Does this confuse you or help you in understanding this comparison?
I just wanted to ask about the introduction rule. So are you saying that if you have a type A and a type B, then if you were to input a type A into your function, it would output type B?
Basically, yes, that's the idea. So here what it says is, this rule says, if I have an input of type A, I have a rule, which I'm going to call it f of A. So this f is really a rule. So an example of this would be this double business, right? So this is an example. If I have some, let's say, a natural number, and I know how to double it, right? That's also a natural number. Then out of this rule, I can generate a function which takes n to 2 times n. But this function lives in a new type. It doesn't live in natural numbers. It lives in these new types, nat to nat. Does that make sense? But
Yes.
maybe we should clarify that these objects, these are types like A and B, while this little a and little f of A are terms. Right? They live in some other type. Okay, so, but we defined double and we checked it. Now we can also evaluate that double, let's say. So if I do double of like 20, then hopefully I get 40. Okay. Let's do a puzzle. Let's try to define a function from natural numbers to rational numbers. which halves that number that we start from. So here's the challenge. I want to define half, function half, and I want to replace this sorry with something. Maybe because I want a function, maybe fun is the first thing. But after that,
would you write would you then define your natural number n?
so I want to give the argument as the input. So this is my input. Sure.
Yes.
And then you would arrow it and say that it becomes n/2, and you would make that irrational.
How do I do that?
You assign it to q.
Right, exactly. So if I do half right now, or maybe better add half, that tells me the object we defined is actually a function from nat to nat. This is not what we want, right? So we want to force the output to be by the way, this is also does not implement the idea properly, because if I do eval of half of 1, I'm getting 0. That's not what I want. I want to have 1. Right? So we better force this natural n, which was first, natural number, to now be considered as a rational number. And now here I get the right type for the function half. And hopefully this is 1/2.
And just to double check, so if the function instead was saying that you wanted to take a rational number and have it, like if n was initially assigned to being q, then you wouldn't need to do that in the second half.
I hope so. Yeah, I think so. So
Okay.
Let's check that out to be sure. So let's say this came from q. And then I just would that work? Yeah, it seems so. So let's test this though. Maybe evaluate. First of all, check maybe. So it goes from q to q. What about evaluating this at, let's say, 3/4? Oh, wait. What? No, sorry. To write half at evaluated at this is not good, right? What is going on here?
Maybe it's the parenthesis.
Sorry, it was my mistake. I should have written eval.
Oh.
It does give the right output, right? Because half of 3/4 is 3/8. And we can do another test, maybe. I don't know. Do you have a number you want to put in here? Maybe 1. 1 also works, because 1 is a rational number as well.
And if you put in 2, it would still say that 2, it would give you 1 as a rational. It wouldn't give you 1 as a natural number. Like it doesn't automatically lift it.
That's right.
Okay.
You can also check that, because what you're asking is essentially what is the type of this, right?
Mm-hmm.
I think that's right. So that's a rational.
Yeah, thank you.
No problem.
Okay. So when you're checking a function, you have to add the little at before it, right?
You don't have to necessarily. When you do this, you get so it outputs as a rule what the function is, right? Rather the type of the output, right? It says if you give me an input of rational, my output, which is the whole thing, half rat of n, it's a rational number, right? That is basically the same thing as saying the whole rule or the whole function is from rational number to rational number. It just doesn't have this arrow.
I see.
Right. So here's an example where we are taking, right. So I wrote a comment here which says, if I write a function like this, maybe I put a comment here. If I write a function like this, and I check it, and maybe I put an add for more explicit version. Okay, it says it's a function from integers to integers, right? But didn't we say that if I don't put a type for n explicitly, then the default type would be natural numbers? So what is going on here?
Is it because since natural numbers are non-negative, if you were to add a negative, it would automatically then cast it to the next available, which is an integer?
Absolutely, that's the correct explanation. So because the output is a negative number, the input could not have been a natural number. And the next available type after natural numbers that has negatives is integers, as you exactly said. But perhaps this doesn't give me the, although the function is perfectly defined, well defined, maybe it doesn't really have the number. So maybe the naming is not correct, because I think if I eval this at, let's say, 1, oh, I get -1. And that's not what I want, right? What is going on? So output is -1. But really, I wanted -½ rather. Does anybody know what's going on here?
Is this the same thing where, like, because it thinks it's going to be an integer, it's just taking the floor
Absolutely, yeah.
when you like divide it by 2?
Yeah, so the floor is essentially the largest integer below a certain fraction, right? So the floor of -1/2 would be the floor of -½ which is -1. So this is the floor of, yeah. Which is not what we want. We want, perhaps if we wanted the actual half, maybe we should have written as half. Actually, what should I have done if I wanted like the output of this to be -½
Would you cast it to a rational number?
The input or the output?
The output?
Okay, so I don't, so you're suggesting that I don't specify anything for this, so I keep it as it is. Then the output goes to rational numbers, and then this. So maybe first check what the type of this is. I'm guessing this should be from rational numbers to rational numbers. Okay, so why is this true? Why isn't the first one integers?
Is it because since you output, well, since you casted the output to a rational and didn't define n, it will assume that n is also rational?
That's right. So if I force this n to be a rational number, then the first one also has to be a rational number. That's how I can unify them. So they cannot live in two different types. They have to be unified in one type, essentially. So what went on here, I think I forgot where it was. Yeah, well, what went on here essentially is so once we gave the type of output to be integer, then this first n also has to be an integer, because they have to live in one type.
What if you specify the first n to be integer?
Oh yes, in that case, then this whole defaulting system wouldn't work. So in that case, I think it would. So okay, great idea. So let me just check this, maybe eval this, and then we go to your question. What if I eval this function as 1? In that case, I get the right output. So we answered the previous question. Now we have a question, new question, which is, what if I did this and alternatively, and say that this takes, do you say this to be integer?
Yeah, just specify the first one to be integer, but keep the rest.
And perhaps
Is it going to be like a function from integer to rational numbers?
I think so. Yeah. So
Okay.
what happens is, like, this n here in the output is not the same, but it's casted. And I want to see if we can actually see this. So if I do this, what happens? No, that doesn't help. What if I do reduce? There's a new command, reduce, which looks under the hood a little bit of a function. But I wonder if it works here. Seems not. My link got stuck a little bit. Okay, what if I comment it out? What if I put it back? Oh, that's funny. Okay, this is an unknown problem. I have to investigate this. And also, sometimes it's good when yeah, sorry, go on.
Oh, do you mind expanding a little bit what you mean by like looks under the hood of the function?
Yeah, so
like what is that showing, supposedly?
So let's say, right. So if I just write check sock, then it just gives me this, right? But if I say reduce sock, then it tells me, well, you know, sock was a function that sends n to n plus 1, right? But what is really n plus 1? It's in Lean, it's defined as nat.sock, right? So with reduce, you can actually see what successor is. And now if we want, we can click on this thing. And now you go to mathlib. And this is essentially how natural numbers are inductively defined. So this is a file in mathlib, which is called prelude. It's like, and nat is like maybe the most basic type in mathlib, certainly one of the most basic types. And we haven't got to inductive types yet, but here's the basic idea is like nat has two constructors, right? It's like there are two canonical ways that you can introduce an element of a natural number. It's either that natural number is 0, or it's successor of some other number. So you start with 0, okay, then you have 0, then you can apply successor to 0, so you get successor of 1, right? And then you can apply successor to successor of 1, so you get suc 1, and you can iterate this process. And inductive type essentially means you can iterate a constructor to get more elements. So out of this specification, I get infinitely many elements. 0, suc 0, suc 0, which is 2, and so on and so forth. And this I discovered by essentially instead of check, applying the reduce command, right? Because it tells you under the hood how this sock is defined. Or maybe we can also do nat. So if I have addition of natural numbers, right? sorry, this is not such a good example, but maybe does this tell us more information? Right. So if you do check nat.add, this defines a function like this. So this is already quite complicated. What's happening? Why are there like 3 types and not 2? Because so far we had 2 types, right? Something from A to B. Now we've got like 2 arrows and 3 types. So that's something weird. We have to explain this. We get there. But I just wanted to mention the difference between check and reduce. So check outputs this data for you, right? While reduce outputs all this complicated data, which essentially tells you under the hood how addition for natural numbers is defined.
When would we need to use reduce?
Almost never. So if you'll never, yeah. So I don't know why I introduced it here. I guess I wanted to see under the hood how this casting happens from integers to rational numbers. And I wanted to do reduce, but suddenly my Lean was not helping me. It gets stuck. So this orange arrow means I cannot compile my file. And this is, I don't know why this should happen. And maybe a hint for some tip for future is when you get stuck like this, then you can, if you know what the problem is, then you can comment it out like this, right? Or if you don't want anything after this line to be compiled, you just write exit. And now everything before exit is compiled, so it works, right? And anything after exit has not been compiled, so you don't get anything in info view. But let me comment this out. So this was to compile until this line. And let me also comment this with that. Wait, I'm still stuck? What's going on? Okay. And sometimes when it's rebuilding stuff, even though fast, it's a good idea to go to terminal and to build all the project. So that this way, the new stuff that we have written will be cached out. So next time the build is faster. Okay. Suppose I have a function f from A to B, and I want to take the domain of this function, which is the domain type, which is the input type A, right? So, okay, my input is a function, and my output now is a type. And this we never had before, right? We usually outputted a term of a type. This time we are outputting a type itself. And same with the codomain function, which outputs the type of the output of f. Right. So A is the type of inputs of f, while B is the type of the outputs of. So if I check this, what do you expect for, like if I check code or if I check DOM, what do you expect to get from Lean? Any suggestions?
Will it just output the type?
Just pick type, like TYPE.
You got me there, Professor. I don't know.
maybe this is actually quite close, but not there yet. So if I check this, it does say type. So you were right, but it says a little bit more than that, right? It says that I'm taking two types A and B, and I'm taking a function, and then applying domain to that function gives me a type. So in principle, this gives the type of the output of domain, right? Which is a type itself. But what if I say now check at DOM? So then I get such a thing. So if we ignore these curly braces, which we have not talked about yet, really we have to read it from here, this much. So this is a function of this type. It takes, so this is the type of input. It takes as an input a function from A to B, and its output, it's a type. And the domain, it's an element of that type, is a term of that type. Maybe I write it. So if I go back to my schematics of like how we write these function types, what's really happening is like, you remember I had A and B, and then I can form A to B. But A and B can be really anything, any types, I mean. So if that's the case, then I have this new type A to B, right? So maybe I write it here. Then I have type of all the small types. So that's a type, and this is a type. So this is a type. This is a type. And this is a type. But so here we should be careful because this leads to lots of contradiction, is the Russell paradox. Really what I should write here is saying that the types of one universe lives in the type of the bigger universe, next universe. So there are these universe levels. And to that, you need to say things like this to be consistent. And this U is the level of the universe. But for now, we want to ignore all this. Okay. So again, now we have two types, right? We have this one, and we have this one. So I can apply the function type construction again, and I would get this type. Did I go too fast? Is this too complicated? Please give some feedbacks.
I'm like a little lost. I think when you were describing the universe thing, I was just kind of confused.
Yeah, let's that's confusing. Let's not go there.
Okay, okay.
Let's just imagine that there is this type of all types or something, and I think that for now that's fine. I can just delete these types. Actually, they make it harder to read. Essentially, what I'm saying is like, if I can from A and B, I form the type of functions from A to B, then I have type of all types, and so here's one type. Here's another type. I can form the arrow types, functions from this one to this one. Does that help or not really?
Yes. So like A and B are like, they're just type. They're not like a specific type, like a natural number or anything like that. But could they be like, and if so, could they be two different types?
Absolutely. So these are like just, this is at the very general level that A and B can be any types. But as an example, A and B can be like both natural numbers. And so I would get the functions from natural numbers to the type of all types. So for example, this domain, right, takes a function from A to B, but that function can be suc, right, which goes from natural number to natural number. So in that case, the domain of suc would be a type, because domain sends something from A to B, something from nat to nat to a type. And indeed, which type is this? Well, we can eval that. Ooh, well, I have to evaluate at something, I guess. Wait, what's going on? Okay, so this is another interesting issue. We cannot evaluate types, we can evaluate terms. So there is a problem here with evaluation of this expression. But modulo that, essentially the domain of successor would be just a type of natural numbers. Maybe reduce would have helped in that case. Ah, yeah, that helps. So that tells me that the domain of successor is not. There was a question, I think, no?
What happens? What if like A was irrational and B was like a natural number? Like, then what would the type be?
So just to be clear, you mean A and B types of natural numbers and types of rational numbers, or a natural number and a rational number?
Does it make a difference?
Yeah, so the difference is this essentially, right? So one half, let's say, is a rational number, and Q is the type of all rational numbers, right? So here in this diagram, let's say, this A and B are types. They are like this bit, right? And what is going on with, like, let's say, so for example, this can be NAT. This can be NAT. This is NAT. To NAT. And here, so for example, in this type, only in here, there's an element suck, right? And there's an element in here, you know, which takes a function, let's say suck, and takes its domain. So if my suck lives in here, then the domain of suck lives in here. And that in this case would be just, you know, the domain would be a natural, the type of natural numbers. If no more question, I go on with this. Okay. So we specified one way to, you know, one sort of syntactical way to specify functions, but there's a simpler way, which is, so if you remember, we defined double as sort of like, you know, to a function like this, fun, nat, then there was this arrow to 2 times n. So if I define it again, yeah, like that, lean, sorry, wait, what's going on? Yep. So it gives me an error that double has already been defined. So I cannot repeat that, right? But that was how we defined double essentially. What I can do is, like, to get rid of this arrow guy, just give the input and the output. So this is the second way. So you can bring this input thingy and write it before this definition sign. So this is a second way to specify functions. So here's another way to define double. I'm writing double alt. I'm using addition operation instead of multiplication. Is there a question about how we specified this function? What's the difference between the second way and the first way? So the difference is, like, I'm eliminating an arrow and I'm putting the input inside here.
Would there be a case where one is better than the other, or it doesn't matter?
Doesn't really matter. I like this. This is just syntactically simpler. I like this one. Like, and this is like how you write functions in Python and other languages, essentially. Unless you like arrows, in that case, you should go with arrows. So it's just matter of style, I would say. I think maybe, yeah, I mean, the other case also has this word fun, right? Which immediately when you see that, you know it's a function. While for this, you might think a little bit about that. For example, if it gets complicated. I mean, there can be advantages to either side. But this definitely has less words in it, and it's simpler. By the way, you can also write this n times n just in front of it. Doesn't have to be the next line. Okay, so this is a function that squares a number. I want to skip this point and come back to it later in the next lecture. The part about functions have to be total. And I want to get to a third way, which is we can define functions by something called pattern matching. So let's say that I have defined a type. So I'm defining a type here called type of weekdays. So this is an example of an inductive type. But really, what was going on here is like I'm saying, let weekday be a type which has only 7 terms or 7 elements in it. So Monday is a weekday, Tuesday is a weekday, and so on and so forth. So if I check weekday, I get a type. And if I check weekday.monday, then the type of this is weekday. Does this make sense so far?
Yes. What does the dot do?
So essentially, if I look at NAT also is similar version of this. It's a little bit different, but it's an inductive type which has infinitely many elements, while this is an inductive type that has only 7 elements. So if I go to NAT, so you see that NAT has 2 constructors. One is 0 and the other one is sock, right? And here, if I want to access any of those 2 fields, then I write nat.0. And this essentially accesses 0 inside NAT, because potentially there can be many different zeros. Like 0 of integers. In that case, you would have check int.0. So what we are doing is we are accessing 0 in the type NAT. So here, when I write weekday.monday, I mean Monday defined as a term in this type. And also I can do like check weekday.sunday, right? Also, I can define another inductive type like that. And maybe not weekday anymore, but weekend. And here, I would have Saturday and Sunday. But notice that now there are 2 terms. I can do weekday, Saturday, or I can do weekend, Saturday. These are 2 different elements because they live in 2 different types, right? So this dot notation essentially gets Saturday from 2 different types. Does that make sense?
Yes, that does. Thank you. Is there a difference if you did like when you identified the Monday to like your weekdays, you did the semicolon weekday versus for the weekend, you just did Saturday, Sunday?
Not really. I mean, here I was just being too pedantic. So you could have deleted this bit. It would have understood from just the syntax with this, space and putting this bar here. It would have understood that this Monday belongs to the type that I'm trying to define. because essentially what I'm doing is like I'm defining a type as a collection of bunch of elements. So it would have understood that these things are elements of that type. Yeah, if you like, you could have done this, and not for the second one, although not stylistically, maybe not the best. But anyway, what's happening? I deleted that accidentally. Right. Now here's a function that goes from the type of weekday to type of Booleans. So Booleans are type that has true or false, right? And when I said we can define functions by pattern matching, I mean, if I want to define a function from weekday to Boolean, so what's the idea of this function, first of all? I want to say, specify which days are lecture days for this course, right? So I want to say Tuesday is a lecture day, Thursday is a lecture day, but Monday is not, right? So therefore, I take an argument from this type. Well, that's one of these things, one of these days, right? And I'm saying if that day is a Tuesday, return true, which means there is a lecture on that day. If it's Thursday, then also return true. And if it's any of the other 5, which I say whatever, this is a way to write whatever. Underscore means whatever. Whatever the other day. That's input. Return false, which means essentially that there is no lecture on that day, right? So if I do check at is lecture day, I do get a function that goes from weekday to bool, and that's what I wanted anyway. Does this make sense? So maybe I finish by a puzzle. So I want to define a function from Booleans to Booleans, which switches true and false. So it sends true to false and false to true. How do I do this? Anybody wants to comment on this?
Just write Boolean dot true arrow into to false.
So bool dot false.
Yes, and Boolean dot false arrow to true.
Right. Great. Because again, Booleans are, if you look at Booleans, like command and click, essentially, it says inductive. So it's an inductive type, which has 2 elements, right? It's like a weekday, but instead of having 7 elements, it has 2 only. And in this case, I think because this Boolean is part of Mathlib, you could have, I think, gotten away by just this. Yeah. So you don't need to specify true and false. And like, you know, if you eval now switch at false, you get true. So, okay, I don't want to go much over time, and I want to stop here, but just saying that there is more in the demo that I would recommend you to read, although I will go over this on Thursday. And you should also look at the source file of this function, because that has many more examples. And also let me put this warning that the next homework, just because we are dealing with more interesting objects, which are functions, is going to be more colorful. Any questions, concerns, comments before? No question?
Yeah, Professor, do you have time to have a little meeting after like tomorrow's section? I'm still a little bit stuck with like installing like Lean onto my Mac.
Oh no. Yeah, sure. I have time. I have time right now after this meeting, but I don't know if
yeah, I do. Yeah, I know. I have another class after this one, so
so yeah, let's meet after the lecture tomorrow.
yeah, absolutely. Thank you so much.
Okay, great. Let me stop recording here, and then if there's a question you want to ask after the recording, also, let's see. Wait, how does one stop record? Yeah, stop.